So to continue with this exercise, second derivative test, well, we've got the second derivative, hypercritical values, test the values. So we need to test these values in the derivative. Well, we can test the derivative in either this form, but I think it would be easier to test it in the second form. Or, well, anyway, it's fine. All right. So that's let's use the second derivative. So that's a 12 times -1 minus 12 times -1 squared. That means, well, -1 squared, which is +1 times -12, that's -12. And then, so -12 minus 12, that's a -24. Well, this is a negative number. So the sign of f double prime in the first interval is negative. What about the second interval, the one in the middle? So for that, let's test the derivative, the second derivative, 12 at 1/2. Well, in this case, so 12 times 1/2, that's a 6. And well, -12 times 1/2 squared, but 1/2 squared is 1/4. So 12 times 1/4, that's 6 minus 3, which is 3, which is a positive value in this case. Well, that the function or the second derivative is positive in this middle interval test. And let's finally test x equals to 2 in the derivative. The second derivative, rather, 12 times 2 minus 12 times 2 squared. So this will be 24 minus, okay, 2 squared, which is 4, 12 times 4, that's 48 minus 24, equals to -24. And in this case, this is negative. Well, so write down a negative sign. All right, what is our conclusion in this case? When the second derivative is negative, it's concave down. What about positive? Concave up. And again, concave down. All right. So let's write down symbolically. Concave down, concave up, and concave down. All right, it goes sad, happy, sad. Well, it changes from concave down to concave up. That means this is going to be an inflection point or a turning point. Well, there's another turning point here for x equals to 1, because that changes from concave up to concave down, or vice versa, doesn't matter. Well, so we're going to have 2 points of inflection for this function. So those 2 points of inflection, and again, just to be clear, what did we do here? Test in f double prime. To find the points of inflection, we go back to and plug them in the original function f of x. Okay, so we need to compute f at 0 and f at 1. So what's the original function? Okay, I need to scroll up all the way to the original function, 2x cubed minus x to the 4th power. So 2x cubed x to the 4th. So that is 2 times 0 cubed minus 0 to the 4th. Well, that's just 0, so the point of inflection is 0, 0. That's the origin. And what about 1? So that's 2 times 1 cubed minus 1 to the 4th. So that's 2 minus 1, which is 1. And that corresponds to the order pair 1, 1. All right. Okay, how about we do a summary? So after, because we will be working with these exercises for a while, so I think it's worth to look at a summary. And in the summary, I will just include the relative extrema, that is relative max and relative min, and points of inflection, if any. All right, so I think we got a relative max. but we didn't get any relative min. So relative max 3 halves 27 over 16, 3 halves 27 over 16, no minimum, and the points of inflection 0, 0 and 1, 1. How about we verify this using our graphing calculator? So this will be alright, so I need to change the mode, I guess, as usual, to function and clear. And what is that again? It's 2x cubed minus x to the 4th. X to the 4th. And let's graph. Okay, is that graph? Okay, let me do some zoom box. No, I don't think that's gonna be okay. Zoom box. And some units to the right, some units to the left. Oh, come on. Zoom box. Okay, I'm gonna do it here. Oh. Okay, I just want to focus on this part of the graph. All right. So, concave down from negative infinity to 0. Does that check with the graph? Concave down, and then concave up from 0 to 1. From 0 to 1, concave up, and then point of inflection, and again concave down, and it goes, turns upside down, and that becomes a concave down. Now what about relative extrema? Okay, for relative extrema we got a maximum point at 3 halves, which is essentially 1.5, and whatever that value 27 over 16 is. So this x value where we have the maximum indeed seems to be 1.5 or 3 halves. Alright, and whatever that value is, it's almost 2. Doesn't matter. And what else? Point of inflection, the origin and the point 1, 1. So did you see how this point is where the graph changes from concave down to concave up, and that point 1, 1, that's where the function changes from concave up and then becomes concave down? So I think the graph actually confirms everything we got by hand. Right? So let's go about another example. Let's analyze f of x equals 1 over x. So number one, we cannot differentiate this function while x is in the denominator. So f of x equals x to the negative 1, and f prime of x equals to negative 1 x to the negative 2, which is negative 1 over x squared. So when we set the derivative equal to 0, so individually we need to set the numerator equal to 0 and the denominator equal to 0. But in this case, well, for the numerator is negative 1 equal to 0. Well, that doesn't make sense. So all we have to do is x squared equals to 0 and x equals to 0. So 0 is our only critical value here. All right. So 0, that's going to give rise to 1. and 2 intervals to test. So that's why I have 2 blank columns here. So number 1, define the intervals negative infinity to 0 and 0 to infinity. Well, so let's choose our favorite test values. A number less than 0, what would be a good number? A number in this interval. Negative 1. What about the second interval? Positive 1. Alright, so we're going to test x equals to negative 1 and x equals to 1. Alright. So in this case, so we need to test this again in f prime, not in the original function. So that is negative 1 over negative 1 squared. That's going to give us negative 1. And negative 1 over 1 squared, that's also negative 1. So in this case, what are we going to obtain? Negative and negative. So that means decreasing and also decreasing. So in this case, we're not going to have any max or any min. In fact, even if we had any change between increasing and decreasing, or vice versa, decreasing to increasing, that'll be an issue because that number is legitimate, not in the domain of the function, because if you observe this function, x cannot be equal to 0. Alright? Nevertheless, we can still analyze the function, check the end behavior of the function before and after that number that it's still excluded from the domain. Alright? And well, so what do we have? Relative maximum, relative minimum, NA. Not applicable, not applicable, none of those. Alright? We don't have anything. Just intervals where in fact just decreases. Well, can we verify this using the graph? Of course. I'm not going to go to the graphing calculator because I think this one is an easy one to graph. That's 1 over x. That's just this graph, isn't it? So in this case, well, notice how this first tail of the graph is decreasing, and so is this, right? It's always decreasing. And this is confirmed analytically using the first derivative test. Alright. Let's look at the second derivative test. So the second derivative of the function, well, number 1, the first derivative was negative x to the negative 2. Find the second derivative. That's going to be positive 2x to the negative 3, 2 over x cubed, and set 2 over x cubed equal to 0, and the only critical number is x equals to 0. Or rather, not critical. This one is hypercritical number. So, well, we're going to use a very similar table. That's going to look the same. And in this case, well, let's define the intervals negative 1 to infinity. Negative infinity to 0 and 0 to infinity. So, and that's because the hypercritical number is 0. That's going to be the two. These are going to be the 2 intervals that we will test. So we need to check some of the test values. And again, I'm going to use the same ones as before. Negative 1 and positive 1. And well, let's determine the sign of f double prime in this case. Well, so we're going to test negative 1 and 1. Where are we going to test this again? Well, since we're looking at the second derivative test, we're going to test in f double prime. That is 2 over negative 1 cubed. That's going to be 2 over negative 1, which is negative 2. So that's, well, what about x equals to 1? 2 over 1 cubed. That's 2 over 1, which is 2. So for the hypercritical value, x equals to negative 1, we got that the second derivative is negative, and for x equals to 1, the second derivative is positive. This means that concave down and concave up. All right. Graphically, concave down, concave up. That means there's a change in the concavity, which suggests that there is an inflection point, right? Because there's a change in the concavity, there's a turning point. However, is x equals 0 even in the domain of the original function? So there's really no inflection point. So here is a note that we want to write in this case. Even though there is a change in the concavity, which suggests the existence of a point of inflection, which I will just abbreviate POI, point of inflection. That point is not in the domain of f of x. So, no point of inflection. And here is where these kind of problems get a little tricky. Yes, I mean, I'm actually seeing that it's changing from concave down to concave up, or vice versa. But the issue here again is that for that hypercritical value, it's not defined in the original function. So even if you see a change in the behavior, which suggests the existence, but a point of inflection, well, it's not a point of inflection because there's nothing in the original function. All right, and well, points of inflection, NA. And I'm not going to do a summary of this because, well, we didn't get a maximum nor a minimum, and I don't need to look at the graphing calculator because we already did this one by hand, and that verifies the results, right? Let's look at another example, one involving exponential functions, all right? So how do we deal with exponential functions? Well, number one, let's find the first derivative. Let's do everything related to the first derivative test. So that's f prime of x equals 4e to the 2x times 2 by chain rule minus 4e to the negative e to the 4x also by chain rule. And simplifying this is going to be 8e to the 2x minus 4 e to the 4x. All right. Well, in this case, we need to set the derivative equal to 0 to get the critical values. That is 8 e to the 2x minus 4 e to the 4x. Set that equal to 0. All right, so we have this exponential function. And well, in this case, it would be great that we had the same coefficient for both exponential terms. That way we can do, okay, so for example, what if both were 8 e to the 2x minus 4 e to the, or rather, 8 e to the 4x equal to 0, okay, that's 8 e to the 2x equals 8 e to the 4x. Cancel the 8, e to the 2x equals e to the 4x, and take ln to both sides to cancel the exponential. That would have been great, but that's only if we had the same coefficients. However, that's unfortunately not the case, all right? And because that's going to be 8 e to the 2x equals 4 e to the 4x, e to the 2x equals to 2, or rather 1/2 e to the 4x. So in this case, we cannot do the ln thing, unfortunately. All right, so we have to go in a different route. Question?
So the 4 e to the 4x, did you do the channel?
Yes, that's the 4 multiplying in the front. And I had the 4 which was originally there, but the 2 from the chain rule I put it afterwards for the first term. So in this case we cannot go that route. In this case we will have to go about solving this equation by factoring. Well, in this case, you know, like when we factor, you know, 8x squared minus 4x to the 4. Suppose we want to factor this polynomial to solve the equation. So the GCF would be for the numbers. What about the 4? For the powers of x, x squared. That's going to leave us with 2 minus x squared. All right? Are you guys following me here? All right. So how do we apply this to these exponentials? Well, in a similar way, however, with exponentials, not with polynomials. So this is going to be, I'm going to factor a 4 e to the lowest power of the exponential, or the lowest exponent of the exponential, that is e to the 2x, times 2 times, or just 2, and then minus e to the 2x equal to 0. Okay, let's do the distribution back into it. So 4 times 2, that's the 8 e to the 2x times, so that's just e to the 2x. But over here, 4 times negative 1, that's negative 4. E to the 2x times itself, e to the 2x. Doesn't that result back into e to the 4x? Alright, so that's the equation that we will solve. And we're going to use the zero product property to solve this equation. That is 4 e to the 2x equals to 0, and 2 minus e to the 2x equals to 0. Well, e to the 2x equals to 0, but try to take ln of e to the 2x, that's fine. But what's ln of 0? Isn't that undefined? So recall that exponentials never go to 0. So let's see what about the second equation. So that's e to the 2x equals to 2. Take ln, and that's going to be cancel 2x equals ln of 2, and x equals 1/2 ln of 2. So that's the only critical number in this case for this function. Alright, so only one critical number. I'm going to draw that number line next to the table here. In fact, this critical number, 1/2 ln of 2, which, let me briefly do an approximation using a calculator. I believe it's 0.693 over 2. So ln of 2 over 2, 1 point, oh, no, ln of 2 divided by 2, 0.34, 0.346. That's approximately the critical value. Alright, so this will divide the real number line into two intervals to test. That's why, again, I have only 2 empty columns here to fill in the blanks for. So negative infinity to 1/2 ln of 2, and 1/2 ln of 2 to infinity. Alright? Test value. So let's choose our favorite value. What would be a good value right here? 0. Alright? 0. What would be a good value in the second interval? 1. Alright? Sounds good. Okay. So test x equals 0 and x equals to 1. Where? In f prime. Alright. So f prime, which is 8 e to the 2x minus 4 e to the 4x. So 8 e to the 0, or rather e to the 2 times 0 minus 4 e to the 4 times 0. Well, this is going to be e to the 0, which is 1, times 8, and e to the 0, which is 1, times 4, that's 8, minus 4, which is 4. This means this is positive. What about 1? Alright, so 8 e to the 2 times 1 minus 4 e to the 4 times 1. Alright, so this is going to be 8 e to the second power minus 4 e to the fourth power. So, well, I don't have a way to tell by just looking at the numbers that this is positive or negative. However, I'll have to do this using the graphing calculator. So I have 8 e to the second power minus 4 e to the fourth power, and that's actually negative 159.28. So negative. Alright, this means negative, and conclusion, increasing, decreasing. So there's an actual change from increasing to decreasing. What does that suggest? Well, concavity, that's for second derivative. Alright? Yes. There's going to be a maximum because we're going up the hill and then down the hill. That means we are eventually changing from, we are reaching a maximum value. Alright? So, well, that relative maximum will be, well, we don't have any minimums, NA, we can just do that. So find the relative max and relative min in the original function, not f prime, right? In f of x. So our original function, which is 4 e to the 2x minus e to the 4x, 4 e to the 2x minus e to the 4x. So that's going to be f evaluated at 1/2 ln of 2. And well, this one is going to be a little weird one, but it's going to reduce very nicely. So that's 4 e to the 2 times the quantity 1/2 ln x minus e to the 4 times the quantity 1/2 ln x. Alright, let's reduce first. The 2's cancel here. That's going to leave us with 4 e to the ln of, not x, actually it's ln of 2. So that's going to leave us with e to the ln of 2 minus 4, minus e to the 4 over 2, that's 2 ln of 2. Alright, so in the first term, we can reduce e with ln, and we can multiply 4 times 2. However, we cannot cancel the e and the ln for the second term while we have the 2 as a coefficient. So we need to use the basketball rule for logarithms, make that coefficient be a power. So that's going to be number 1. 4 times 2 minus e to the ln of 2 squared. Cancel the e with ln. That's 4 times 2, which is 8, minus 2 squared, which is 4, and that's 4. So we have a relative maximum at the point 1/2 ln of 2, comma 4. Alright? We will verify this at the very end. So let's find the second derivative. So for the second derivative, we got that the first derivative was f prime 8 e to the 2x minus 4 e to the 4x. Finding the second derivative, that's 2 times 8, which is 16, e to the 2x minus 4 times 4, 16 e to the 4x. Well, so our dream just became true from last time. You know, this time we're gonna have the same coefficient, so this equation will be a lot easier to solve. So set this equal to 0 to find the hypercritical values. So that's 16 e to the 2x equals 16 e to the 4x. We can divide out the 16s. Oh,
That scared me.
so yeah. And well, so once we divide both sides by 16, we get e to the 2x equals to, I'm going to leave a space here, e to the 4x. This so I can do ln and ln on both sides. And we do that to cancel ln of e. ln of e, 2x equals 4x. And be careful how you solve this equation. How would you solve this equation? 0 equals 2. Would we divide both sides dx? Is that a good way to go about this equation? What happens if we do that? Divide both sides by x. 2 equals to 4. Since then it's equal to true. It's equal to true. This is not true, right? So that's not the correct way to go about this equation. So to have all terms, negative 2x equals to 0, x equals to 0. So what we did before about dividing both sides by x, it's potentially dividing by 0. And what happens when we divide by 0? That's undefined. So that's our hypercritical value. And that's x equals 0. That's going to give rise to two intervals to test. And again, those intervals are going to be negative infinity to 0, 0 to infinity. And let's choose test values. And well, we already looked at these values, so that's negative 1 and 1. And let's test them. So we are going to test this again in the second derivative, f double prime. So that is so in the second derivative, this is 16 e to the 2 times the negative 1 minus 16 e to the 4 times negative 1, that is 16 e to the negative 2 minus 16 e to the negative 4. This will be approximately, okay, let me do this in the calculator. So this is 16 e to the negative 2 minus 16 e to the negative 4. And that's going to give us a positive 1.87. And 1.87. And in this case, for x equals to 1, so that's going to be 16 e to the 2 times 1, which is 2, minus 16 e to the 4 power. Well, oh, that's going to change a lot. Because actually the exponents are positive. And well, notice the exponent in the second term is bigger than that in the first term, so that's going to be approximately negative 755.34. I don't care about the actual value actually, because these are only test values. This means greater than 0 and this means less than 0. So that's only to determine positive and negative. That's a concave up and concave down. All right, in other words, it's going to go from happy to sad. That implies the existence of a point of inflection, and in this case, this hypercritical value x equals 0, it's actually in the domain of the original function, because the original function, which is an exponential function, doesn't have any issues with 0, doesn't have any restrictions. So let's go ahead and find that point of inflection where, again, in f of x, the original f of x. So that is, we will have to evaluate this at f of x equals, what's the original function again? 4 e to the 2x minus e to the 4x. F of 0, 4 e to the 0 minus e to the 0. That's 4 times 1, which is 4, minus e to the 0, which is also 1, and that's 3. So the point of inflection is 0, 3. Let's verify the results looking at the graph of the function. Alright, so that's 4 e to the 2x plus e to the 4x. Let's look at the graph of this function. And I need the whole graph. Zoom, standard 6. What happened here? Oh, I believe it was minus, right? Oh yeah, that's gonna change a lot. So let me zoom fit. No, that's not gonna help. Zoom standard. I will have to do zoom box again. Well, no, that's fine. Zoom box. Do enter. Okay, this is a little slow, but we will be there eventually. So I want to magnify at least the portion of the graph we're interested in. Alright? So, okay, that's fine.
Out of curiosity, is there a reason you don't use a program like Desmos for the graph?
Yeah, the reason why I try not to use the internet while I'm recording is that slows down my recording sometimes, and I get some lag sometimes. Well, so let's check. So we have a maximum at the value, where is it? Where's the maximum? ln of 2, comma 1/2 ln of 2, comma 4. So the y value of the maximum is 4, isn't it? Isn't it confirmed by the graph? And that x value right here, I mean, it's not even a half. It's not even a half. So that's the 1/2 times ln of 2. And what else? So we have a point of inflection where at the point 0, 3. So it goes concave up. And here at the y-intercept, that's 0, 3, that graph becomes concave down. All right? It goes to concave down, and it's also increasing and decreasing from that critical value. All right? So that actually confirms our calculations. All right? And let's see. So there's one more exercise. However, I think I'd rather do this on a different time.